Hi, everyone. Today we are focusing on a combined section 5.1 and 5.2. 5.2 is about definite integrals, and 5.1, we're going to hit some stuff that is about the limit definition of the integral. So we're going to start off with a definition here. So an integral is, as we've been talking about like yesterday, we were talking about area, how you're finding area. An integral is a way to find area. So if a function y equals f of x is non-negative, and integrable basically just means can be integrated over a closed interval from a to b, then the area under the curve of y equals f of x from a to b is the, and then here's the new word, integral of f from a to b. Non-negative gives you the area under the curve on that interval. Okay, a couple of things we need to do here is to get the information and the way the integral is written understood. Okay, so the first thing is that this here is the integral sign. So it is what tells you to find area. Then a and b here are your lower bound and your upper bound. And the f of x is your integrand, is what we call it. It's just what you're integrating. And dx stands for the variable of integration. So if we were looking over at this thing over here, I don't know what the function is, so I'll just call it f of x. But this function, we could say we're finding the area. So we'd write integral from a to b, but really I can use some numbers there. So let's say from 0 to 2 of this function f of x, and we're integrating with respect to dx. So this is how you would see, how you will see things written when we're talking about integrals. Okay, so let's do a couple of practice problems here. Oh, before the practice problems, let me just go a little bit further with some understanding. So if the function is non-positive, meaning that's below the x-axis, so less than or equal to 0, then you can think of the integral from a to b being equal to the negative area underneath the curve or between the curve and the x-axis, or you can think of area being equal to the negative or the opposite of the integral. This is because area is always positive, okay? Just like speed is always positive. An integral itself can be negative, just like velocity can be negative. It tells you, it would give you the location of your function where it is at. But when we talk about area specifically, we want to talk about it being positive. Okay, so these first examples we're going to do are not actually going to be area that we're looking for. We're just looking for the integral, and all we know right now is how to do this geometrically. When we say confirm on our calculators, it just means you could graph it and look at it on the calculator. All right, so here's our first example, the integral from 3 to 7 of 3 dx. This is just, there's a couple ways to do it. So I'm going to start by drawing a quick little sketch of this. So if I were to graph 3 from 3 to 7, so that is this horizontal line, which makes a rectangle that has a length of 4 and a height of 3, which is where the 12 comes from. But the other way you can do this is you take, if it's just a number, you take the number and you multiply it by the difference between the upper bound and the lower bound. So 7 minus 3, oh my gosh, excuse me, times 3. All right, next one. So I'm going to show you the answer and see if you can make some sense out of it here. So -8 is the answer, and if we use what I just suggested to you, you are doing -2 times 7 minus 3, which is 4 times -2, which is -8. You can also think again of creating a rectangle, and the rectangle is below the x-axis, which is where the negative comes in. And this is 4 this way and -2 this way, which is a -8. Last one is also 12 for the same reason we've been doing. So 4 times 1 minus a -2, 4 times 3 is 12. Okay, so now we're going to do some, again, geometrically. So that when we say geometrically, what we're asking you to do is to draw a graph or draw a picture of what's happening. So you have to have a little bit of understanding of what's going on in the problem. So I'm hoping that as we move farther along with these radicals, you'll start to understand that this type of a radical situation is asking or is talking about, excuse me, the equation of a circle. So it starts off as x squared plus y squared equals 16. So y squared equals 16 minus x squared. And then we're taking the square root of both sides. And so our function is the square root of 16 minus x squared. Now this problem only wants us to integrate it from -4 to 0. So you're thinking of a circle, radius 4, centered at the origin. So it's got 4 quadrants that it's working in. But I only want the part that's from -4 to 0. So that graph looks like this. So from -4 to 0, it is 1/4 of this circle with a radius of 4. So 1/4 of a circle pi r squared, radius is 4. So 1/4 of 16 pi is 4 pi. Okay, next one. So this is absolute value equation that's been flipped upside down and also been shifted up. So we want to make sure we know what that looks like, and then we want to find the area underneath that thing. So this graph, here it is, it looks like a triangle. So we're finding the area of that triangle by using the formula 1/2 base times height, if I can get rid of that. All right, so 1/2, don't know why this little blue box won't go away. There we go. 1/2 times my base is 2. My height is 1, so the area is 1. Okay, next one we're going to draw a graph of here. It's the line 4x is what we're starting off with. But then we're going from 0 to b, which all that's really telling you is you're going to be creating a formula. So from 0 to b. Okay, so the equation from 0 to b, just a line. This would be b here. And then this height, because it's on the line y equals 4x, the height is 4b. So then the area is 1/2, it's a triangle, 1/2 times the base b times the height 4b, simplified is 2b squared. Okay, so the next one we have here is this weird equation of x over the absolute value of x from -2 to 3. So let me first get rid of this picture, this thing here, and here's the picture that we have. So this is the equation, but there's something that you can't really see in the equation here, and that is the fact that there are holes at here and here, because you can't have 0 as a value. So this causes an issue with our definition, which if you were to go back and look at or listen to the video again, you'd see that the definition of the integral is the area under the curve, but it is integrable over a closed interval. Well, this interval is not closed. It is open because of this part right here. So this one just is not possible. Okay, moving on. So now we're going to do some stuff with some problems that are like the area is given to you and you're going to use that information to help you solve it. So you're told in this problem that the integral from 0 to pi of sine of x dx is 2. So I've drawn this graph over here for you. So this whole entire area underneath the blue part is 2. So then we want to use what we know about sine curves. We want to to use the know what we know about sine curves to figure out some areas. So this is the sine curve it's the other part of the sine curve. So instead of going from 0 to pi, which is here, it's going from pi to 2 pi. It's the same amount of area, it's just below the x-axis. So this answer is -2. Now this one, kind of pay attention to how this all worked here. So everything from the original problem, at least here and here, has been shifted to the right 2. So my lower bound went to the right 2, my upper bound went to the right 2. And then using what you learned and know about transformations, remember from last year, y's are y's, x's are not so y's. X's do the opposite of what you think. So this x is also going to the right 2. So the sine curve has been shifted to the right 2. The bounds have been shifted to the right 2. So therefore, it's the same exact region. So it also has an area of 2. Okay, a few more. I did graph these already for you here. So now we're going from 0 to 2 pi. So remember, from 0 to pi has an area of 2. This is the same region below the x-axis. And since it's below, it's negative, so it's -2. So if I just add those two together, I get 0. Okay, and here's the same function. We're using u instead of x. It doesn't matter as long as these two match. Again, this region is 2. Same region just below the x-axis. It's a -2. So -2 plus 2 is also 0. Okay, now we have some changes a little bit, but I hope as we go through they make some sense. So this one, here is the graph for you again, is half of the region we were talking about. So this one is half of 2. So this is 1. All right, I am just gonna, I think I'll go over here to 6 because we'll just go in order. So notice what happened is we stretched, again, think transformation. We stretched out the x bounds. So the normal sine curve goes from 0 to pi for one like loop. Now it's gonna go from 0 to 2 pi for one kind of upper part of it because of our transformation. Again, y's are y's, x's are not. And we also then stretched out our bounds. So my sine curve is going to have the same region now from 0 to 2 pi, and my bounds went from 0 to 2 pi, so this answer is 2. Okay, so now this one, there's a couple of ways to think of it. Here's the graph. Oops. So if you were to think of this as, well, I've got a rectangle, and I've got that sine curve. And that sine curve's area is 2, and the rectangle has a length of pi and a height of 2. So this area is 2 plus 2 pi. Or you could separate and have two integrals and use the rules that we know about each of those. So instead of doing it geometrically, you could do this with some previous rules. So this one is the one where if it's just a number, you take the number and you multiply by the upper bound minus the lower bound. And then this one we already know. That was what was given to us. That's 2. Either way, the answer is 2 plus 2 pi. All right, number 8. So here's my cosine graph. Should look familiar because it's basically the sine curve, right? Just shifted. So this has nothing that we need to calculate. This is just equal to 2. Number 9, we have taken the sine graph and we have stretched it. Okay, so here's the graph of it. It's a little bit harder to think of geometrically. So instead, what I'm going to do is kind of give you a new, hopefully logical rule. I'm going to pull that 2 out front of my integral. So just take my constant and put it out front. And now I have the sine curve from 0 to pi, which is 2, we already know, multiplied by 2, which equals 4. And then last one on this slide, here is my cosine curve. You can see, I hope you get, that this would be 1 because it's half of that sine value. And then this is below the x-axis, so it'd be a -1. Add them together, you get 0. I know I went through them kind of fast, but I'm hoping that as I'm speaking, if you're not getting it, you're pausing and thinking about it and writing it down and writing down any questions you might have as you're listening. Okay, moving on. So now we're moving on to, it's not really in your book, so this is something you need to pay close attention to. It's on your book because our book is old, but it is an AP topic that's been added. So it's something you'll want to be paying close attention to. Okay, so, gosh, excuse me. Basically what we're doing is just like when we did the limit definition of the derivative, we are trying to understand what the limit definition of an integral would mean. So keep in mind that an integral stands for area. So we need to have some way of understanding that we're finding area. So if you look at each of these little pieces here, the if you look at, like, if I see if this makes sense. So if you remember from last year, this sign, this is the summation sign, this means to add stuff up, okay? So what you're adding is you're adding up rectangles. So this piece here, the lovely f of ck, which is what they call it, I would not have chosen that. That is the height of your rectangle, and then delta x, that would be the distance along the x-axis. That would be like the width or the base of your rectangle. So you're doing base times height, then this is adding them up, and then the limit is saying, all right, well, what would the area be if I took an infinite number of rectangles? So I made the rectangles so small that they were just paper thin, okay? So that is what each piece of these stand for. So then we have to figure out a way to take a function, write it in this limit definition notation, but also be able to write it as an integral. Hopefully the integral part is the easy part. So we're going to look at example 1, and we're going to do the integral part first. So the bounds are from 2 to 5. So those go here. The function goes inside 2x plus 1, and then dx goes here. Done. So writing it as an integral is easy. The writing it as a limit part is a little bit trickier. So we're going to follow this procedure over here. Remember, this is not in your book, so please make sure you're taking these notes down. So the first thing you do is you find delta x. Okay, delta x is, again, the base value of your rectangle, right? So the rectangle would be the upper bound minus the lower bound divided by the number of rectangles you're trying to create. Well, we want to have an infinite number. That's why we're calling it n. So my delta x in this case is 3 over n. That's step 1. Step 2 is we're supposed to find an expression that is going to basically stand for x, like something that's going to be 2x plus 1 in our problem, okay? So we are going to start by picking something to stand for like our first value, where our first rectangle would start, where our second rectangle would start, and then writing it for the k term rectangle, okay? It says this can be done from the left or from the right. What that means is you can think of LRAM or RRAM. Do you want to use rectangles from the left side or rectangles from the right side? Initially, it always feels easier to start on the left side, which would just mean that C sub 1 would be your left bound, but it actually works out better if we think of it as being an RRAM situation. So, and I know this gets confusing, and remember, you're not supposed to master this right away. So go, listen to the video again, and then we will talk a little bit about this tomorrow in class. Okay, so if I'm going to use RRAM, that means my first rectangle would start at 2 plus whatever I've decided my delta x is going to be. And then the next rectangle would start at 2 plus another delta x, or 2 plus 2 delta x. And my third rectangle would be 2 plus 3 delta x, and so forth and so on. So that means that C sub k would be 2 plus, well, I need to have, my subscript is k, I need to have k delta x's. So whatever rectangle I'm on, I want to multiply that number by my delta x. So this becomes, if I fill in my delta x, 2 times k, or 2 plus k times 3 over n. Okay. Then I take this thing and I substitute it into my original function of 2x plus 1. So it's going in for x. So this here is going to go in. Don't tell Mrs. Roderick, but I'm writing plug in for x because that's faster than substitute. All right, 2 times, and then here's my x, 2 plus 3k over n plus 1. This simplifies into 5 plus 6k over n. this 5 plus 6k over n gets multiplied by the delta x. But we're not actually going to multiply it in. We're just going to leave it like this. So then this whole thing, the first parenthesis goes here, and the second parenthesis is your delta x, and it goes over here. So you're always going to have the limit as n goes to infinity of k equals 1 to n, the sum of that, and then it's 5 plus 6k over n goes here, and then times 3 over n. So this is my final answer of writing this integral in the limit definition form. All right, I'm going to do another one, and then if depending on how long I've been at this, I might stop. We'll see. I don't want the video to go too long. Let's see where we're at. All right, so the next one, same type of problem. Get the skinny marker here. So my integral, again, the integral part's the easy part. From 0 to 4, those are my bounds, and then my function goes here, x squared dx. Okay, but we need to write it as a limit definition. Okay, so the first thing you're supposed to do is find delta x. So delta x is upper bound minus lower bound divided by n, so 4 over n. Then the second thing you're supposed to do is find your c sub k that you're going to substitute in. So find something that's going to represent what you're going to use to find the height of each rectangle. So it always is best if you do your RRAM. So that means you're going to take the left bound, which in our case is 0, and add on delta x. And then c sub 2 would be, well, 0 plus 2 delta x, which means my c sub k would be, I'm not even going to write 0, it's going to be k times delta x. But I know that delta x is equal to 4 over n. We already found that. Okay, so now I'm supposed to find the lovely, my favorite, f of c, k. And that is then substituting c sub k into your function, which is x squared. So then this becomes, where am I at? Lost my train of thought, sorry. 4k over n quantity squared, which I'll simplify that into 16k squared over n squared. All right, so that is my f of ck. Then I have to, I think I'm going to skip step 4. I think you guys can understand step 4 is just taking this and multiplying by delta x. Okay, so my final answer is the limit as n goes to infinity of the sum when k goes from 1 to n of 16k squared over n squared, all times 4k over n. I'm sorry, it's not 4k over n. I have too many k's. It's just 4 over n. Sorry, I just realized I wrote that wrong. Okay, so we're going to do one working backwards, and then again, I'll see what time it is. So we're just going to do number 1. I've given you the answer to number 2. So what you're trying to do is figure out what this limit is as an integral. This is most likely how you would see it on the AP test. They're going to give you the limit definition, and then they're going to expect you to figure out how to turn it into an integral. Some of you might be able to look at this and totally see what's going on. Other people need a little bit more, steps to do. So I'm going to kind of work backwards from what you saw when we did the other problems. So I want you to think of this part here being delta x, and remember delta x is always upper bound minus lower bound. And there's a variety of bounds you can use, but pretty much unless there's something that's glaringly different, it's going to be 0 as your lower bound. So that means my upper would be 1. So 1 minus 0 over n is my delta x, which means my bounds are from 0 to 1. And then we're going to, again, work kind of backwards. So knowing that c sub 1, now my left bound would be 0 plus 1 delta x. And then that means my c sub 2 would have been 0 plus 2 delta x, which means my c sub k would have been 0 plus 2 times 1 over n times k. I forgot my k. because there's a K in here, right? Not, oh my goodness. I am not starting this video over. You guys are going to have to deal with I just made a mistake. Sorry. It's like the third time I started the video over. I'm not starting over. So it is, we'll ignore the 0, and it's not going to be a 2. It's going to be K times delta X. And delta X is 1 over N. So my C sub K is K over N. So then we're looking in the problem to see where you're seeing a C sub K going on in here. So I see one here, and I see one here. And remember, this is what gets substituted into your function. So that was what was substituted into a function, and it was put in this slot, and it was put in this slot, which means your integral should have gone from 0 to 1, and K over N is really an X value. So now that is 2x squared plus 1. And remember, delta x was 1 over n, but really delta x is just dx in our situation here. So that is the answer to number 1. I'm going to leave number 2 alone. I think maybe you can figure it out. If you, maybe not right away, but maybe you can come back to it. At least the answer is there for you. I'm going to do one more with you, and then we're going to stop, and we'll pick it up tomorrow with any questions you might have. I'm going to do 3 with you because 3, notice, doesn't have a delta x in the problem. It hasn't been factored out. So I need to factor something out so that I can actually have some way to figure out what my bounds are. So when I look at this, I see that if I factor out a 4 over n, that could be my delta x with my bounds. So if I factor 4 over n out of 12 over n, I'm left with a 3. And then if I factor 4 over n out of 8k over n squared, I'm left with 2k over n. And then this is again 4 over n, and that gives me, if you think of that being delta x, that gives me bounds going from 0 to 4. Okay, so now again, I'm going to work backwards. And I'm doing this in a lot of steps. You could probably streamline this as you get better at it. So left bound is 0 plus 1 delta x. C sub 2 would be 0 plus 2 delta x. C sub k is then k delta x, but delta x is 4 over n. So it's 4k over n. Okay, now the problem then, I think that the extra problem here is that I don't have a 4k over n in my problem. I have a 2k over n. So I need to rewrite the stuff in parentheses so that it has a 4k over n. So what I'm going to do is take that parenthesis now and rewrite it with the skinny pencil. 3 plus, and if I factor a 1/2 out of the 2k over n, I am left with 4k over n. So I'm rewriting it so that I have a 4k over n in my problem. So now, okay, bounds are from 0 to 4. 3 doesn't have anything to do with 4k over n. So that's there. And remember this thing, the c sub k, that is your x. You're looking for that in the problem because that's going to be filled in with an x. So this is just 3 plus 1/2 x. And remember, this was your delta x, which in the world of integrals is dx. So dx goes there. I hope that's starting to make some sense. Make sure you've written down any questions you have. Feel free to try the remaining problems. I'm going to go ahead and show you the next couple. I think I have answers to a few more here. Let's see. So there's the answer to 5, and there's the answer to 6. You do not have to try them tonight unless you want to. I hope that you might at least give one of them a try, and then we can come back together tomorrow and see how it went. See you tomorrow.